Winter did not arrive gently at 8,000 feet in Wyoming's Wind River Mountains. It arrived like a verdict. Jacob Petro learned that truth in December of 1884, when frost crept across the inside of his cabin walls and his water bucket froze solid less than 3 feet from a roaring wood stove. At night, ice feathered along the log seams. By morning, his breath still hung in the air. Jacob had built exactly as every homesteader was told to build. Tight-laid logs, mud and moss chinking, a raised plank floor. A cast-iron stove hauled up from Cheyenne at great expense. Nothing fancy. Nothing foolish. Just the trusted frontier formula that promised survival. And yet, by February he was losing. He burned more wood than 2 grown men should need in an entire winter, waking each dawn stiff, aching, and shivering. Across the valley, his neighbors fought the same battle, feeding their stoves relentlessly while the cold pressed in from every direction. The mountain winter didn't care how hard you worked. It only cared about physics. That spring, while others repaired fences and planned their planting, Jacob began something different. Quietly. Deliberately. He applied his grandfather's old-world masonry knowledge to build what neighbors soon mocked as a ridiculous clay oven bed. They laughed, until the next winter came. While nearby cabins remained cold and devoured cord after cord of firewood, Jacob slept warm through sub-zero nights, using barely half the fuel. In the next few minutes we're going to break down exactly why that worked, and what Jacob understood about heat that nearly everyone else had missed. Frontier wisdom followed a simple rule: build fast, build cheap, get shelter before the snow flies. Every homesteading guide preached the same gospel. Cut whatever timber you could. Lay a rough stick floor over log joists. Throw up plank walls. Drop a cast iron stove in one corner, punch a straight pipe through the roof, and trust that fire would do the rest. Mail-order catalogs even promised miracles. One popular wood burner claimed it could heat any cabin up to 400 square feet. Most settlers took those promises as law. Jacob did too. His cabin measured 16 by 20 feet, with 7-foot walls chinked tight against the wind. The floor sat on joists spaced 4 feet apart, leaving gaps wide enough to swallow a coin. His iron stove stood in the northwest corner, pipe rising straight through the roof. A narrow wooden bed platform occupied the far corner, raised 18 inches off the floor for safety. Within 20 miles, nearly every cabin followed the same blueprint. And nearly every one failed the same way. By late December, problems became impossible to ignore. On clear nights, condensation formed on the interior walls, freezing into thin sheets of ice by morning. The plank floor conducted cold so efficiently that standing barefoot became painful within seconds. Worst of all was the temperature imbalance. The cast iron stove blasted intense heat within arm's reach, while the far corners of the cabin hovered below freezing. Jacob's bed, kept deliberately distant from the stove to reduce fire risk, remained brutally cold. He woke every morning stiff and sore, buried under quilts that never truly warmed. His neighbors fared no better. Down the valley, Thomas Brennan burned through his entire winter wood supply by early February and resorted to breaking furniture for fuel. Mary and Samuel Curtis watched their infant develop a persistent cough from breathing damp, smoky air night after night. Old Henrik Larsson's roof began to sag beneath the snow load because the cabin stayed so cold that no interior heat ever rose high enough to melt accumulating ice. Everyone blamed the mountains. Jacob blamed something else. Jacob possessed knowledge most frontier settlers did not. His grandfather, Dmitri Petro, had been a master stove builder in the Carpathian Mountains of Eastern Europe, regions where winters routinely punished families far more severely than Wyoming ever could. As a child growing up in Pennsylvania, Jacob had listened to stories of massive clay and stone ovens that heated entire cottages. These were not stoves in the American sense. They were thermal machines. Dmitri described masonry heaters weighing several tons, filled with internal channels that forced hot exhaust gases to travel long, winding paths through stone and clay before ever reaching a chimney. Families cooked their evening meals, then slept atop benches built directly into the heated mass. One fire. All-night warmth. To frontier ears, it sounded absurd. When Jacob mentioned these systems at a winter gathering in Thomas Brennan's cabin, the reaction was immediate. "We ain't building castles out here," Brennan scoffed. "We're trying to survive, not show off fancy European nonsense." Samuel Curtis added that masonry required lime mortar and skilled stonework, neither of which existed on the frontier. And who, he asked, had time to haul tons of rock when land still needed clearing? The laughter was loud, confident. But Jacob saw something they didn't. The real problem wasn't the cold outside. It was how quickly heat vanished inside. Cast iron stoves heated air fast, but air holds almost no heat. The moment the fire slowed, warmth fled up the chimney and through countless cracks in the structure. Raised floors allowed cold air to circulate underneath. Thin plank walls provided almost no thermal resistance. The entire system produced violent temperature swings, 40 degrees or more between a roaring fire and dead ash. Heat was being created, and immediately wasted. Jacob began sketching ideas in a leather-bound journal his grandfather had given him years earlier. What if, instead of heating air, he heated mass? What if stone and clay absorbed heat slowly and released it over hours? What if the sleeping surface wasn't isolated from warmth, but became part of it? The stories came back to him clearly. Clay-coated stone benches. Bodies resting directly against stored heat. Warmth that lasted until morning without feeding a fire through the night. The challenge was adaptation. Old-world masonry heaters relied on fired bricks and lime mortar, materials unavailable in the Wind River Mountains. But field stone was everywhere. And Jacob knew how to mix workable clay mortar from local soil. The materials could change. The physics did not. His neighbor's skepticism ran deeper than practicality. Frontier culture prized speed, mobility, and temporary solutions. Many settlers expected to move on once claims were proven. Heavy masonry implied permanence, and permanence felt risky. Sleeping on stone sounded primitive, even backward. Jacob understood that he wasn't just challenging construction habits. He was challenging an entire philosophy of survival. Through January and February, as others burned through precious wood and endured bitter nights, Jacob quietly gathered field stone and tested clay mixtures by the creek. He worked alone, observed patiently, calculated carefully. By early March he had collected enough stone to begin. Dense pieces from a talus slope 2 miles east, chosen specifically for hardness and resistance to cracking under heat. The clay he found nearby turned plastic when wet and cured hard as cement. To begin, he did something that horrified his neighbors. He tore up part of his floor. And that's where the real experiment began. Jacob began by tearing up his pine plank floor and cutting straight down into the frozen earth beneath his cabin. Using the largest, flattest field stones he could lift, he formed a combustion chamber roughly 2 feet wide, 18 inches deep, and 20 inches tall. The walls rose 12 inches above floor level, with an arched opening facing into the cabin. The opening was deliberately smaller than the chamber itself, 14 inches wide and 10 inches high, to regulate airflow and maintain proper draft. But the firebox wasn't the innovation. The breakthrough was what happened to the heat after the fire burned. Instead of letting hot exhaust rush straight up a chimney, Jacob forced it to work. From the rear of the firebox, he built a hidden flue system, a maze of stone channels that trapped heat inside the masonry mass before allowing smoke to escape. The first channel ran horizontally along the base of the structure for 6 feet. Then it turned upward into a vertical passage. From there, it reversed direction and ran horizontally again, forming a slow S-shaped path through the stone. Every turn bled heat from the exhaust gases into the surrounding masonry. Each flue channel measured 6 inches square, large enough to prevent blockage, but narrow enough to maximize contact between hot gases and stone. Jacob formed them by laying flat stones as channel floors and walls, capping each section with heavy slabs before stacking the next layer above. Every transition had to be smooth. Sharp corners or uneven joints would disrupt draft and choke the system. This wasn't brute force construction. It was precision. The most radical element came next. Instead of building a separate wooden bed frame, Jacob made the bed part of the heater. As the masonry rose, he extended the final layer beyond the firebox, creating a flat stone platform 6 feet long and 3 feet wide. Beneath it, the hottest horizontal flue channels passed directly underneath, separated from the sleeper by just 4 inches of stone. This was intentional. The stone absorbed heat all evening, then released it slowly through the night, directly into the body above it. To support the weight, Jacob used massive capstones, some weighing over 100 pounds, forming an even sleeping surface. Below them, he packed smaller stones tightly with clay mortar, creating thermal mass while protecting the flue passages beneath from collapse. Mortar became the system's lifeline. Pure clay cracked as it dried, so Jacob experimented relentlessly. His final formula used 4 parts blue clay, 2 parts sand, 1 part chopped grass, and 1 part wood ash from his stove. The ash improved bonding and reduced shrinkage. This mixture dried hard, sealed tightly, and resisted cracking under heat. He pressed mortar deeply into every joint, then smoothed the interior flue surfaces by hand. Soot buildup would destroy efficiency. The gases had to flow clean and steady. The chimney connection was calculated with equal care. Jakob positioned the final exit at the highest point of the flue labyrinth, 18 inches above the sleeping platform. From there, an 8-inch square clay-lined chimney rose vertically through the roof. The total flue length, from firebox to chimney exit, measured nearly 24 feet. That distance mattered. Every extra foot extracted more heat before smoke escaped into the mountain air. Testing began on a mild March evening, with temperatures hovering near 20 degrees. Jakob lit a small fire using dry pine kindling and split aspen logs. Within an hour, warmth began radiating from the stone platform. The draft pulled cleanly, no smoke entered the cabin, no backflow, no choking. When the fire burned down to coals, Jakob laid his hand on the stone. It was hot. By his estimate, the surface reached 90 degrees Fahrenheit. More importantly, it stayed warm. When he woke 12 hours later, the stone still radiated heat, roughly 70 degrees by feel. Fuel consumption dropped dramatically. The entire heating cycle used roughly 1/8 of a cord of wood. His old cast iron stove had required twice that, sometimes more, just to survive the night. This system captured heat that iron stoves wasted straight up the chimney. The finished structure weighed nearly 2 tons. That mass was the secret. It heated slowly but cooled just as slowly. Instead of wild temperature swings, the cabin experienced steady, even warmth. No roaring fire. No freezing ashes by dawn. The neighbors noticed. Jacob's chimney smoked less. His woodpile shrank slower. Thomas Brennan remarked that Jacob must not be heating properly. Few understood what they were seeing. But the masonry bed exposed a deeper problem. While the stone stayed warm, the cabin itself leaked heat relentlessly. On calm nights, the system performed beautifully. But when wind swept through the valley, cold air poured in through every crack, between logs, around the door, beneath the floor. The heat escaped faster than even 2 tons of stone could replace it. By April, Jakob identified every failure point. The mud and moss chinking had dried, cracked, and fallen away, leaving gaps as wide as 2 inches. The door warped and leaked. The window glass rattled loosely in its frame. Cold air flowed freely beneath the raised stick floor. The heater worked. The cabin didn't. And that realization led Jakob to the next phase, one that would seal warmth inside and finally break the mountain winter's grip for good. Jakob wasn't finished. His masonry bed kept him warm, but the cabin itself still bled heat like a sieve. The stick floor, raised on open joists, funneled cold air beneath his feet. Gaps between logs yawned, and the thin plank walls offered no real barrier against the bitter Wind River winter. To truly harness the heat, he needed an envelope as clever as his masonry stove. He turned to the old techniques of German and Swiss settlers he had known as a boy, methods for weatherproofing log cabins using materials available on the frontier. The first innovation was a superior chinking mixture. Jakob combined 4 parts of the same blue clay used in his masonry work with 2 parts sand, 1 part chopped straw, and, most surprisingly, 1 part cow dung borrowed from a neighbor's herd. The organic matter prevented cracking and added binding strength. With care, he pressed this mixture deep into every gap between logs, eliminating hidden pockets of cold air, and smoothed it flush with the log surfaces. But that was only the start. Jakob's revolutionary step was applying a continuous clay plaster across the entire interior wall. He remembered seeing this in the homes of German immigrants. The walls themselves acted as a thermal sponge. He mixed 3 parts clay, 2 parts fine sand, and 1 part finely chopped grass, adding just enough water to make a workable paste. Then, working in small sections during warm afternoons, he applied it 1/2 inch thick, pressing it into the wood grain to ensure adhesion. Patience was everything. Rush the plaster and it would trap air bubbles or crack as it dried. Each section took 2 full days to cure, during which Jakob carefully maintained cabin temperature to prevent rapid shrinkage. When complete, the walls acted as a second thermal mass, absorbing warmth from the masonry bed and radiating it back slowly, long after the fire had died. Windows and doors posed additional challenges. Jakob designed a double barrier system for the window, first sealing gaps with heated pine pitch mixed with clay, pressed carefully into place, then adding removable interior shutters built from split pine boards. Between the shutters and glass, he inserted wool batting salvaged from old clothing, creating an insulating airspace. Doors required similar care. Jakob trimmed the frame, carved grooves along the edges, and pressed strips of wool felt into the channels. For the coldest nights, a heavy wool blanket hung on pegs added an extra layer of protection. Entry became slightly inconvenient, but warmth was worth it. The floor, however, was the biggest breakthrough. The raised stick floor had acted as a massive cold bridge. Jakob blocked airflow underneath with a vapor barrier of overlapping birch bark sheets, then packed 6 inches of dried grass and pine needles atop it. This created a lightweight insulative layer, cutting off the chill from below while preserving the structural integrity of the floor. The results were immediate. The plaster walls absorbed heat from the masonry bed, radiating it evenly through the cabin. Drafts were gone. Cold corners disappeared. The combination of thermal mass and airtight sealing maintained consistent temperatures throughout the space, a sharp contrast to the wild fluctuations created by conventional iron stoves. Spring rains revealed another advantage. Whereas bare log walls absorbed moisture, creating mold and dampness, the clay plaster stabilized humidity. It absorbed excess moisture when the air was damp and released it slowly when the air dried, creating a healthier, more comfortable indoor environment. Fuel efficiency skyrocketed. Alone, the masonry bed had cut wood usage by roughly 50%. With the new sealed envelope, fuel consumption dropped nearly 70%. One evening fire now heated the cabin through the next day, even in chilly spring weather. Thermal mass plus proper insulation worked together in a way that neither could achieve alone. But the system had new demands. The masonry flue labyrinth, excellent at storing heat, created numerous surfaces for condensation and soot accumulation. Humid conditions could form water inside channels, risking structural damage. Improper fire management could coat the stone with creosote, threatening a dangerous chimney fire. Jakob's original 8-inch square chimney, adequate for an iron stove, proved insufficient for his labyrinth. Smoke sometimes backdraft into the cabin during storms. He rebuilt it, applying lessons from a traveling mason he had met the previous summer. The new chimney rose 24 feet above the roof, built with flat stones and high-quality clay mortar. Internal dimensions measured 10 by 12 inches, 30% larger than before. The interior was lined with sand-washed clay, smooth enough to encourage laminar flow and resist creosote buildup. At the base, he added a specialized smoke chamber. Exhaust from the labyrinth collected in this chamber, slowed, deposited remaining particles, and then accelerated smoothly into the vertical shaft. Turbulence was eliminated. Draft was consistent, even during high winds and low atmospheric pressure. Fuel selection became critical. Unlike iron stoves, which burned anything from green wood to trash, the masonry system demanded carefully seasoned hardwoods, oak, maple, and ash. Softwoods like pine were limited to kindling. Each piece was split to uniform 3 to 4 inch thickness, ensuring consistent combustion. Wood had to be dried for at least 18 months to burn efficiently, producing maximum heat with minimal smoke. Fire management itself was transformed. Rather than a continuous low fire, Jakob used batch burning. He built a single intense fire each evening, letting it burn completely to coals before adding more fuel. Kindling was arranged in a grid to encourage airflow, then larger logs added progressively. The firebox was sealed with a cast iron door salvaged from his old stove, creating a controlled, high-temperature burn that minimized creosote formation and maximized heat transfer to the masonry mass. Ventilation was precise, not accidental. The sealed envelope reduced natural air exchange, which meant Jakob needed a routine to manage moisture and indoor air quality. Each morning, he opened a small leeward window for exactly 15 minutes, allowing humid air to escape without cooling the thermal mass significantly. On damp days, he extended the ventilation slightly to prevent mold growth. By combining masonry, insulation, airtight sealing, fuel preparation, and disciplined fire management, Jakob had transformed his cabin into a frontier furnace. It was warmer, more fuel-efficient, and far healthier than any iron stove setup his neighbors relied on. This wasn't magic. It was observation, adaptation, and the careful application of centuries-old thermal principles. A forgotten knowledge finally married to the harsh realities of the Wind River Mountains. By midsummer, Jakob's masonry system was running like a well-oiled machine. Ash removal had become a weekly ritual, critical for maintaining airflow through the labyrinthine channels of his firebox. Unlike conventional iron stoves, where ash could accumulate for weeks, the masonry bed demanded constant attention. Jakob used a long-handled wooden shovel to remove ash once it reached about 2 inches deep, taking care not to damage the clay mortar joints.